So our next presentation will be, I'm going to share my screen. And I know I don't have the perfect title here, but Advaith has, the more detailed title on his slides. But Advaith has been working on using machine learning and deep learning to help improve tennis serving. And Advaith is a high school student at the Dunbar High School. So take it away, Advaith.
So hi, my name is Advaith and I'm a rising junior at Dunbar High School, and my project is on developing a novel computer vision-based algorithm to assist tennis players in improving their serve. So currently the way that we have coaching is extremely flawed. There's over 500 times more tennis players than there are coaches, and this severe gap leaves many aspiring tennis players without a coach. Additionally, in light of the COVID pandemic, methods of contactless and socially distant training are needed. Even without social distancing, tennis coaching can be extremely expensive, costing up to $60 an hour. On top of this, self-training just doesn't work, as you end up practicing the wrong stroke, and with no correction from an expert, you end up continuing to practice the wrong technique. The current method of personal training involves manually starting matches and one-on-one coaching with like a coach that you would have. And some of the issues with this are there's a small sample size of historical data, so there's just not enough matches for you to review, and you need experienced coaches, and therefore you're limited by your coach's knowledge and biases from your coach. Currently, training solutions like this are currently available, but they're only available to the elite, and the results often have to be interpreted by a coach, as well as being very expensive. In short, the purpose of this research is to create an ML algorithm that can be used to analyze a tennis serve and provide diagnostic feedback to the player so that no human intervention is needed in training. So some background information about the serve is that it's the only shot where the player completely controls the outcome, so it's not influenced by the opponent whatsoever. And it involves a throwing motion combining the limb and joint movements known as the kinetic chain. An effective serve maximizes this kinetic chain. Throughout all serves eventually reach what we call the trophy position, which is the optimal position for creating the most elastic power. My research question was whether or not we can use machine learning to help tennis players diagnose their serving issues using smartphone footage so that they can practice and perfect their serves without the physical presence of a coach. And my hypothesis is that they can, with at least 50% accuracy. This is the framework that I used to build my algorithm. So we're going to go into some of these steps more later in the slideshow. So the first step for building the algorithm was data collection. So I collected 2 videos each from 17 participants to make up my data set. And participants were asked to serve in the same position every single time. And a local professional tennis coach was actually asked to review the serves and judge what the issues of the serve were so that we can use them in the machine learning algorithm to create labels. Additionally, the statistics of each of the top 100 male and female tennis pros were collected from the ATP and WTA websites and will be later analyzed in R, which is a programming language for statistics. Step 2 of building the algorithm was data preprocessing. So for this part of the algorithm, we used a pre-existing CNN/RNN model known as MediaPipe, which is developed by Google. MediaPipe allows you to draw joints and bones onto the body to give a visual representation to the user, as well as in the backend, pull the X, Y, Z, and visibility metrics for each of the key joints and record them each frame. This is what the main algorithm uses to predict the issue with the serve. So as you can see, we end up with an image like what's on the left, and we can convert that to a data set on the right using MediaPipe. Step 4 is the training/testing. So the frames in the data set created in step 2 and 3 were then split into categories. And the 3 issues that we took were, we took 3 issues with the serve as well as a new category, the good serve, which doesn't have any of these issues. So now the data set was split into a training and testing set. And the goal of the algorithm was to find patterns in the data in the training set, which it found using random forest classifier. And once each tree found the section of the data that it would support, all of the trees put together their decision, and it would eventually give out a final decision on what the algorithm's decision was. On top of this, after the algorithm was trained, I found a key issue in the bias, which was that all the adults, which were the good serves, were on average taller than the other participants. And so the algorithm may be biased in thinking taller players and better players. To test this notion, I decided to use the R analysis that I collected in step 1 and find out if height actually does influence the serve. So as you can see here, this shows the correlation between service points 1 and height in centimeters. So the graph on the left with the red dots is for females, and the graph on the right with the blue dots is males. So as you can see here, the correlation coefficient, which is this value right here, this 0.35, that's the correlation coefficient for females, and the 0.56 is the correlation for males. So as you can see, there's a much more large correlation between service points 1 for males and height than for females. However, on the other hand, we notice that there's almost no correlation between height in centimeters and the first serve percentage. So in conclusion, a player's height is much more likely to be a factor in good serve in males tennis than women's tennis, and different metrics of the serve are likely to be affected differently by height. However, since a majority of our sample are males, height may be an influencing factor. So in order to counteract this, we normalize the height during the process of training the algorithm. So these are some of the results of the algorithm. As you can see, the algorithm was 70% accurate, which means that 70% of the time it would actually get the right issue with the serve. And so on the left, you can see the confusion matrix. So the 7 test videos were on average correct. So as you can see that the good serve, all 3 were correct, left arm up were correct. And on the right, you can see the value versus feature graph. So that shows what the algorithm found to be the most important parts of the serve to make its decision. So as you can see, in this case, the left wrist X position was considered to be the most influencing factor in making its decision for the value. The next step of building the algorithm was embedding the algorithm. So to provide feedback to the player, the algorithm was embedded into both a website and a mobile app, and they both run on a JavaScript version of MediaPipe, which has the same function, but it has a different visual appearance, as you can see. So once the player uploads their video footage, the algorithm will process and return what it believes is the issue with the serve. If it doesn't fall into any of the issues, it will return a good serve, as you can see on the bottom. In conclusion, the hypothesis was supported because the algorithm exhibited an accuracy of 71%, which is greater than the accuracy of 50%. This accuracy level, although it sounds low, is really impressive due to the overall resilience of the algorithm to the high variance of video data, such as different courts, different times of the day, different sunlight, all of that. This means that the algorithm can be effectively trained to analyze the video footage of a serve and return feedback to assist player in improving their serve without a physical coach. Some idea for future research would be to train and test the algorithm with a far larger data set to improve reliability and accuracy, especially with more female players. Also, I'd like to recognize more technical issues with the serve so that you can have more issues to better improve your serve. Additionally, I would like to expand the algorithm beyond serves and into other strokes, such as forehands, backhands, volleys, the entire game. And finally, I'd like to add more design and advanced features to both the app and the website. Thank you for listening. Also, I wanted to demonstrate how the algorithm worked in real life. So I have the website version up here. So I'm just going to put in a random one. So let's say this one. So as you can see, it processes the video. And it's here, you can see it's analyzing. And you can see here that the issue is that he hasn't left his left arm up throughout the serve. And yeah, thank you for listening. This is my presentation.
Thank you very much, Advaith. Love the demo. Very nice presentation. There's a few questions, so maybe you can make me the host while I ask you the questions. So the first question is, can the video be taken at any angle in Zoom?
So we've only trained the algorithm on a very specific spot. So no, not at the moment. It has to be in a very specific spot.
So maybe with more training, perhaps.
Yes.
And then the other question is, there's a few questions, but I think we only have time for 2. Did you record a video of yourself and try to test it?
Yeah, so I've had a couple of videos of me in the data set, and I've used more just to test the algorithm, see how it's working. And yeah, I have.
Okay. And then the final question, I think, is, do you think putting a tracking point on the racket or the ball would help?
So yeah, I've noticed that about a lot of different projects that I've seen in the past about how they have a hardware device. And I feel like this combined with that hardware device really could serve as a really nice training tool in the future.
Thank you so much, Advaith. Wonderful presentation. Thank you.